Hello, everybody. My name is Mark Chupka. I'm the Vice President for Research and Programs here at the Energy Storage Association. Thank you for attending today's webinar, Safety First, Evolving Codes and Standards for Energy Storage Systems. This webinar is being recorded. Everyone who registered will also receive a link to the recording and slides within the next couple of days. Questions can be submitted at any time via the questions chat box in your browser, and we'll get to those after our speakers finish their presentations. In the text of your question, please indicate to whom you would like your question addressed. All meetings and teleconferences of the Energy Storage Association are held in accordance with our antitrust guidelines. We ask that you abide by these guidelines during today's webinar. The full guidelines are available in the members area of the ESA website. If you are not yet an ESA member and would like more information, you can reach out to my colleague, Brenda Lovell. Membership includes free access to all of our webinars, including many of those that are exclusively for members, among numerous other benefits. Please contact Brenda for more information. Before we begin, I'd like to announce a couple of upcoming ESA events. First, if you want to take a deep dive into storage planning, ESA is offering a seminar on June 16th through 17th. Registration is open, so check the ESA website for information. Also, save the date. The annual conference will be held on December 1st through 3rd in Phoenix, Arizona. It'll be great to see everyone again. Today, we are exploring a perennially important topic, enhancing the safety of energy storage systems. Like all energy technology, energy storage systems pose some risks and hazards. In addition to the prudent operational and maintenance practices, an important mechanism to mitigate these risks are the codes and standards that apply to the manufacture and construction of energy storage systems. These codes and standards define today's safety requirements and are evolving along with the technology to make energy storage systems even safer tomorrow. I'm delighted to introduce a stellar panel for today's discussion, each with decades of experience in energy storage safety, along with codes and standards development. First up will be Sharon Bonesteel, who is the Energy Storage System Codes and Safety Working Group Leader at the Salt River Project. She will describe the current codes and standards along with the revision process that updates the codes to reflect new information and experience. James Trudeau will be next, and he is the Market Development Manager at UL LLC. James will explain the critical role that UL plays in establishing standards that provide the foundation for many of the safety provisions in the evolving codes. Our final presenter is Paul Hayes, who's the General Manager at American Fire Technologies. Paul will examine the process by which new data and practical information is developed on hazards and risks and the opportunities to mitigate them, which informs the revision of codes and standards and thus enhances safety over time. After their remarks, we'll open up to audience Q&A. You can ask questions via the questions chat box at any time, and we'll read those off for the presenters when we get to the Q&A session at the end. Now I'll turn it over to Sharon.
It was the double secret mute button that I missed. Sorry about that, folks. Good morning, Sharon Bonesteel, Salt River Project. Happy to be here. Just a brief bit about me. I'm a licensed architect and a certified building official, state certified fire inspector, and I represent SRP at the Codes and Standards Development hearings and represent them in working with local jurisdictions on adopting those codes that are what help keep us safe. Just to get you warmed up here a little bit with the slide progress, I wanted to talk just a little bit about what we're processing through with codes and standards. Is we're all looking at an evolution. that 69 MG that I had, that was my first car. It was a 4-cylinder engine. Then I moved to a RX-7, which is a rotary engine. And then after a couple of BMWs thrown in there, I ended up with an electric vehicle. And that whole process was, over 50 years. So you kind of have to think about that occasionally, in that we've had UPS batteries for ages. And now that we're moving into lithium-ion and all sorts of other versions of that, codes and standards have to change to follow up with that. But they can't keep up with the change that's happening in the code development or in the battery development. So let's just talk briefly about what are those codes and standards that relate to batteries, their use, their different applications. And there are a lot of different codes and standards. The two primary ones are from the National Fire Protection Association and the International Code Council, and also from IEEE. And you start with Nfpa 855, which is the new standard for the installation of stationary energy storage systems. Currently, the next edition of that is out for public comment. The National Electric Code also goes through revisions every 3 years. The 2020 is the current edition of that. And then we also have IEEE's National Electric Safety Code, which is the code that relates for utilities. And that current 2017 edition has a TIA, or Temporary Interim Amendment, that references Nfpa 855. So there is a significant amount of recognition that 855 is going to be the leading document in terms of safe operation and installation of energy storage systems. Now, the Icc Codes, we call them the I Codes. The current editions are the 2021. A lot of you may recognize the fact that your jurisdiction is perhaps on the 2018. These are also revised every 3 years, and energy storage is mentioned in the residential code, the building code, and also very strongly addressed in Chapter 12 of the International Fire Code. What's the difference between a code and a standard? And I think sometimes they overlap, but a code is a set of those recommended rules. They're mandatory language, and they are adopted, and when they're adopted, they become law. Standards are a more detailed level. They relate to more how you get to those compliance elements. So they're more like best practices, and they can be in non-mandatory language. Either can actually be adopted by an authority having jurisdiction, and that could be a state, or it could be a local jurisdiction, a city, or a county. Once they're adopted by that jurisdiction, they become law and can be enforced with civil penalties and criminal penalties. And a good example of the code versus standard is, in the fire code, Chapter 12 requires battery systems to be listed and labeled in accordance with UL 9540. And Jim will talk about UL 9540 later on. And it tells you the rule that a battery system needs to be listed and labeled. That's the rule. That's what the law would say. But then what the standard does, it tells you specifically what testing you have to go through in order for a battery to be listed under UL 9540. So it tells you how to get the listing to meet those code requirements. And the code development process, I think, is a very interesting one, certainly on the ICC side, and it's a process that anyone can participate in. We recently finished the code action hearings, and these are for proposed changes to the 2021 that would go into the published 2024 code. So we submitted proposed changes. We had open public hearings. We had votes on those proposed changes. Some passed, some didn't. But now all of that goes out for public comment. And anyone can comment, anyone can submit a suggested change to it. And it's very worthwhile to register through the CDP. It's the computer data processing of people working on these codes. It's entirely free. And you can find that on the ICC website. So you put in the public comments, and then we will have another public hearing, and you'll have the ability to testify in support of your code change or testify in support of somebody else's. After that, then the final proposals go for online governmental consensus voting. And this is one of the key differences between the NFPA and the ICC. Only governmental representatives can vote, and their final approvals become what the changes are that make up the 2024 codes. A lot of good links here. You'll be able to get to them when you get the slides, which will be sent out in a couple of days. Good access information on those. Then look at the NFPA process. That process is similar, but a lot of the work is done at a technical committee level. The ICC has code action committees, but they're just another body that's working on proposals. The technical committees at NFPA are actually evaluating proposals, voting within the committees, and discussing the changes that go forth with that. And they put forth a final recommendation, and then that is voted on by the total NFPA membership. Now, anyone can buy a membership, and then you're entitled to vote. So the difference between the ICC and the NFPA is anyone who buys a membership in NFPA gets to vote on these changes. Now, that whole code writing process involves people from all over the country, and all of those people in the country come together, talk about things, discuss it, and then those codes are published, and then they must be adopted by the local jurisdiction. That may be the city, the county, or it may be through the state. So, for instance, you could have NFPA 855 adopted as an overlay code to the International Fire Code or the International Building Code and Residential Code. And all of them address, residential type uses in their residential section. On top of that, you could also have local amendments. In particular, I like to note Phoenix's fire amendments to the 2018 Fire Code, because what they did is, because they were not adopting the 2021 code, and because they felt there was immediate need to improve the fire requirements for energy storage, they did an amendment package that actually brought a lot of the work that had been done to create the 2021 code and what was learned in the NFPA code standard development process into a local amendment document that layered on top of the code they already had. One of the key things that you'll find in the codes that I think is the most important part of all of our safety elements, and this is the idea of pre-incident planning. SRP is currently installing 34 megapacks, 25 megawatts in our one of our substations, and we have met already 3 or 4 times with the local fire departments. We've brought them out, we've walked them around the batteries, we've shown them, we've talked about access, we've talked about how we're going to fight a fire. And all of that comes down to you really thinking through the emergency procedure. Who are your subject matter experts? What are your shutdown steps? How is the fire truck going to access? Where does the fire go? And when is it appropriate to let it burn? So all of those codes and standards that we talked about before, IEEE, NFPA, ICC, they all reference some pre-incident planning in one form or another. And my recommendation is that you take the best parts out of all of those, because it's highly important that we get safe installations of battery. And just a little note, I'm in the lower right-hand corner there with Hunter Clare. He was the first responder at the McMicken incident, and I was so happy to see him out walking around, and he's become a really strong advocate for energy storage safety, and it's nice to have him working with us on this one. What are some of the milestones? Yes, we got that NFPA 855. We've got the fire code. Since 2012, this chapter 12 has been getting better and better in terms of dealing with the issues related to energy storage. In fact, chapter 12 is looking a lot like 855, and eventually I think the fire code will reference 855 and be done with it. Key elements are talking about, scope. Who does it apply to? Who doesn't it apply to? Flammable gases and ventilations were hot topics. And IEEE standards, a lot of good best practices, and they're all constantly updating. You're going to see lead acid batteries kind of finding their place again as they start to look at how they can be used for possible large-scale energy storage. And listing and labeling that Jim's going to be talking about from UL. All of those are very key in us being able to manage the quality of some of the installations. And I think a hot topic going forward is definitely how are we going to reuse those batteries when they're no longer appropriate for the vehicles that they were in? How are we going to repurpose those for a second life? Also, I think people are becoming much more cognizant of what are the end-of-life issues and how are they going to handle those end-of-life issues. And what are the key lessons that we've learned? And these lessons are folded into the codes and standards, but they're also found in just the way we deal with each other in terms of deploying these energy storage systems. If we don't deploy them safely, then we're going to lose this great progress that we've made because they'll get a bad rap, and a majority of them are very safe. So battery incidents affect us all. We need to share that information. I know there's a lot of people who are worried about, proprietary information on that, but the more we share that information, especially when we have an incident, the better we can improve the installations and make them safer. Codes and standards can't keep up with these emerging technologies. So you've got to be able to read those codes and standards and look at the technology you're trying to deploy and make sure you've answered all those hard questions. How are we going to keep this safe? In general, we need to spend a little bit more money on the safety aspects. That includes making the batteries more resistant to thermal runaway, some solid state batteries, finding alternatives to these flammable electrolytes, and put some money in the budget for the first responder training and creation of that pre-incident planning and the emergency response plan, because nobody ever seems to have that in their budget. We are working with the fire departments on our emergency response plans, and a lot of conversation, a lot of meetings needs to make sure those are good. And last, I think, use the right battery for the job. Not all batteries are right for each particular instance. So, don't get caught up in what's the latest sexy battery. Instead, really look at what the characteristics are and make sure you're using the appropriate battery. So that's my contact information. I love to answer questions. I love when people send me cool pictures. I also want to show you a couple of slides that are listings of, come on, move. These are the proposals in the latest code cycle related to electric vehicles. So if you go on that CDP axis and look for code changes related to vehicles, these are the ones. And if you're looking for proposals that are related to energy storage systems, these are the ones that are up for that. So I urge you to become involved with these entities and make your voices heard. And also realize that just listening to the code development process, you learn a lot because a lot of experts are up there testifying with regard to these changes. So thank you very much for your time. And I'm going to now pass it on to James Trudeau.
Good afternoon, good morning, good wherever you are, everybody. I'm Jim Trudeau from Underwriter Laboratories. And basically, I'm going to cover these areas. And guys, time me. I'm trying to keep this under 10 minutes. Now, I have about 35 slides. There is no way I'm going to get to them. I put all those slides in there for your reference later when you get these slides from the ESA. I'm not going to cover them today, but you'll have those there as a good reference, okay? And if I can get the right button to work here. Here we go. That's me. I'm going to ignore that for now. Why are UL standards important? Well, first of all, UL doesn't create standards in and of its own. Okay, we put our name on it and a number, but that's really the collected wisdom and experience of what we call the STP, the Standards Technical Panel members. For example, in energy storage, that's UL Standard 9540, that has over 100 members. And UL has one voting member in that STP. Our job is to be a secretary and herd the cats. Basically, the industry creates these standards, and that's everything from energy storage to solar to coffee pots. You, all the people listening, are responsible for getting these standards made. So we really, really encourage you to be a part of the Standards Technical Panel. Much as Sharon was sharing, be a part of the ICC and the Nfpa as well. We call these consensus-based standards, and they're, number one, constantly being revised by the standards members as they collectively gain experience and knowledge. Let's see, right now we're in the second edition of UL 9540. We're in the fourth edition of UL 9540A, and that is going to continue to happen with any standard. It just reflects the maturing of the industry. Now, standards are referred to by building, electrical, and fire codes, as Sharon just mentioned, and they're relied on by AHJs, insurance companies, and guys, you're going to have to pay somebody. Let's keep those costs down, and lenders to minimize risk and optimize safety. And there's an example with the Nfpa 855 down there. Okay, I'm going to go through these fairly quickly. Some key highlights of 9540. This is really important, guys. This is not a component standard. This is a system standards. I do certification for batteries under UL 1973 or inverters, UL 1741, and pretty much everything that goes into an energy system on a component level has got its own safety standard. But when we put those together, okay, that's when we have a system, and that's the energy storage system standard. And that applies to lithium-ion batteries, flow batteries, flywheels. There's a whole lot of ways you can store energy, and we try to adjust most of those in this standard. And the standard, obviously, as we come up with new technologies, is going to change. So be careful. If anybody says, oh, I have a UL 9540 battery or inverter, red flag. Components cannot be certified under 9540. That's a system standard. Okay. And 9540 can cover all kinds of different energy storage systems, walk-in systems, mobile ones, indoor, outdoor, residential, wall-mounted things on the side of your house. And the applications that energy storage is used for is really growing. And by that, I mean, if you look at NFPA 855, any box of lithium-ion batteries over 20 kilowatt hours in size, guys, think of a 2-drawer file cabinet. It's one of those drawers, that little. Anytime you have that much lithium-ion batteries or more, it's considered an energy storage system. And the code does not care what it's actually used for, okay? So that can be telecommunications, UPS, EV chargers are getting those now a lot to keep the demand costs on the grid down. And of course, all the fairly traditional energy storage applications that we're familiar with. It is a requirement in 9540. We really focus on what we call functional safety and understanding the risks that are involved, okay? This is a system standard. If you think of an energy storage system like a big bunch of Legos you're putting together, we want to make sure that, for example, an error or an alarm indication on Lego number 1 gets all the way through to Lego number 10. A failure of functional safety issues was a major aspect of the 29 major energy storage fires they've had in South Korea over the last couple of years. Okay, these things can be installed in all kinds of different places, and we use the certification to make sure it's safe for that application. And again, I'm going to go through these fairly quick. Here's some installation instructions. You can refer to that in the deck. Come on, mouse, work here. There we go. Okay, 9540A is a testing standard. After energy storage came into play, we were approached by a number of government agencies who were very, very concerned about what is this thing that we got here? And we're really concerned about the fire aspects. And how do I measure what a system could possibly do if it went bad? That's what 9540A is. The bad joke is nobody can pass 9540A. The good joke is nobody can fail it. It's not a pass-fail at this point in the game, although that's being suggested. It's I'm going to force a failure to find out what could happen so that smart people like Paul Hayes, who's going to speak later on, can say, well, given that data, this is what we need to do to make it safe in a worst case scenario. And as Sharon said, they rarely fail, but when they do, they're rather dramatic. So let's use this data so we address those safety concerns and we don't have any problems we haven't planned for. There's a whole bunch of different code criteria that go into it, some of the things that are required under that standard. And again, when we test this, we test at the cell level. An individual cell can be as little as your finger in 18650. That can be very big prismatic or large flat cells like that. We test at the cell level. We heat it up, and you see that temperature rises. At some point, the cell vents, and you can see it typically around 150, 170 degrees, and then it goes into thermal runaway. An NMC-based cell, especially I shouldn't say just NMC, but any cobalt-based cell is especially susceptible to thermal runaway, in that once it gets there, it makes its own oxygen, and you cannot extinguish it. You can suppress that fire, but you cannot extinguish it. So designing safety, understanding that, I mean, cobalt-based batteries have a very nice energy density, so there's value there, but you got to be careful where you use them and where you don't. So you see what happens on the cell level. We've got all kinds of interesting equipment to do that, to capture all those gases. We test at the module level. You take a whole bunch of cells, put it in a box. We call that a module. And then there's all kinds of testing again we do here. When we burn the module, it's going to have plastics and wires, and what gases come off of that. We want to know that for our planning. That's what a module can look like. Obviously, there's lots of different variations for that. Unit level is I get a bunch of modules together. I can put them in a classic 19-inch rack. I can put them against in a package on the side of a wall. Basically, if I get multiple modules together, that's called a unit. And you can see all the different types of ways you could use that right there. Unit level tests, we go for the same sort of thing. We in the cell, we're gathering all kinds of information. We want to know if this thing goes bad, what is it going to affect? How was it going to affect other EES unit level or modules? Is it going to affect the building itself? You know, what's it going to do? So we measure all kinds of heat release. We measure gases that come off it, and that data is given to the design community to make use of this wonderful technology, but to do so safely. And we look at, you know, for performance required. Here's non-residential right here. Here's the residential ones. And again, you'll have these slides so you can refer to these. Now, if I have a large container, we call that is tested, it'll have multiple units or multiple racks inside, and we call that an installation, okay? We test multiple racks in that, and we see, hold it, you put this in a big box, you've got various fire mitigation strategies you're using. Does it accomplish its goal? And we do that kind of testing. These are usually really big and really expensive because you're burning up, you know, a lot of dollars to go through one of these. So we're just extraordinarily careful about setting these up. You don't want to say, oops, I blew that one, let's do it again. You want to do it right the first time. So our many, many decades of fire experiences really proved valuable here. And you can see a picture here. So you've got, you know, everything from clean agents to water to, you know, how do I sense when something's going bad? And sensors can be hydrogen, smoke, electrolyte sensors. There's a whole bunch of different ways to do. These are the sort of things we look for, as well as things like deflagration panels and that sort of thing. And we have, again, some performance criteria we're looking for as we do an installation level test. Now, the report you get from all this is fairly detailed, and I'm going to go through this pretty quick, but it looks like this. And we look for key things, you know, for, you know, what's the design, how was the test done? You're going to get things, you know, all the different gases that are there. It's critical to know, make sure as you're getting this, that who did the testing and where? Did the lab have the proper credentials to do the testing? Did they have staff that's trained on? Did they collect all the information they're supposed to? We've gotten some tests out of China, for example, that show one result of gases at the cell level, another very different bunch of gases at the module, and yet a third very different set of gases that comes off at the unit level. Clearly, things were not done in a uniform way. Look for that, because that's the sort of thing that AHJs and insurance companies are being trained to look for. And if they see those differences, they're not going to give you that permit. They're not going to give you that insurance policy. So be really a good consumer as you're looking for testing services in this area. New York City came up with what I thought was a really good solution. You know, you hand one of these 9540A reports, it's, you know, 100, 150 pages. It's pretty data dense. And the average building instructor, he's not an electrochemist. So what New York Department of Buildings did, they said, okay, if you're going to turn in an application for an energy storage system in New York City, yeah, I want you to send, you know, give me a stamped document from a PE in New York State who has fire protection experience, and that would be like members of the Society of Fire Protection Engineers, that sort of thing. And, you know, basically you've got a PE who put his stamp on it saying, yep, I saw the data, I see how they're going to install it, and it'll be safe. And that really takes all the pressure off the AHJ. Now, you're not going to do that for every residential system, but for the larger ones, it's a nice solution. Repurposing batteries. Okay, this is an important topic. Most of the 5G cell sites in China are using repurposed EV batteries. About a month ago, there was a fire and explosion at a large 25 megawatt energy storage system in Beijing. that was powered by repurposed LFP automotive batteries. Now, LFP is supposed to be safer. Well, this large system went bad, and LFP cells can vent gas, which is horribly explosive. Electrolyte gases are typically about 40% more explosive than propane. So if I filled a space with these gases, because a failure of some sort had occurred, and there's an ignition, well, you've got a very big bomb. I guess, and it was bad. 3 people were killed in Beijing and more injured. So we need to be really careful. Well, UL, again, in cooperation with a whole lot of stakeholders, came up with the UL 1974 Repurposing Standard. We're not measuring that battery is good or that battery is bad. What 1974 does, it lays out a standard process for people to evaluate batteries. Now, once I've evaluated it, it's safe, it's good, now it gets retested under the applicable standard. If you're going to use it in a stationary application, it's got to be 1973 approved. If you're going to use it in a mobile application, it's UL 2580. So this is a standard for the process of evaluating repurposed batteries. But then you use, beyond that, the normal battery test standard, so you know that it's safe. It's going to be really, really important. And that's it for me. Now I'm going to continue on and hand it off to Paul Hayes, who's got a lot of very, very good practical experience in these areas. Paul?
Good afternoon, good morning. Thank you, Mark and ESA. Thank you, Sharon and Jim, for your insightful information. I'm very honored to be working with you guys to advance the safety. So I got to take a second on my image here because it's meant to create discussion. There's nothing implied. It is just what we use as our corporate image. And as a fire protection engineer, this is what I make my living doing. So I look at unintended consequences. You know, I very much support this industry, but I'm the guy at the end of the day as a fire protection engineer that has to take all this code, 9540 information, and make it work. So it is part of my job to assume things are going to go wrong, to evaluate the hazard, and work to mitigate that. So I'm going to try to put about 10 pounds in a 5-pound diaper here to get us to questions and answers and discussions. But one of the things I look at is unintended consequences. This to me represents a lot of times what I deal with as a fire engineer. Somebody needed energy. They took a junction box, apparently it caught fire, so they added a suppression system. One of the fundamental issues we deal with batteries is that there's 2 different criteria. One is explosion and one is fire, and they tend to cause problems for the other. So it's a unique hazard that we deal with in this industry. And as probably most are aware, there's been a number of incidences here recently across a lot of different types of systems, types of energy storage, batteries, and the failures were a little different in each case. Some of them, as he mentioned in China, was a very large DC coupled system. Michigan happened to be while they were installing it. So there's been a variety of failure mechanisms. One of the things I have to look at when I'm trying to do safety evaluation is there's a lot of players in this space. The end user sets the expectation. There's an EPC company that has to build it. There's a container company that may be in the US, maybe in China, trying to meet US codes. Our battery manufacturers are all working to come up with a safer product, and that factors into it. Ultimately, the HJ, what are they looking at to protect the first responders? Then we have engineers, developers, and somewhere this has all got to mesh into a cohesive safety package. So where does that safety and cost impact come from? And right now, the industry is a little bit diverse on this. It's kind of like pushing a string uphill. We're trying to get all these pieces to come together through code, recommendations, best practices. As you see, there's a lot of questions that have to be asked. We try to look at a risk-based assessment. And traditionally, my statement was fire systems designed based on a reasonably anticipated event. I've had to modify that a little bit to say explosion and fire. and it makes it a little bit more difficult to evaluate that risk. But ultimately, a reasonably anticipated, unfortunately with lithium-ion, an explosion is a reasonably anticipated event. What I don't want to get into is a zombie apocalypse. So we have to make a realistic assessment of what we're going to see and how we mitigate those. So we try to take a practical approach, but we have to look at this alphabet soup of data that's available to us from an HMA, hazard mitigation analysis, fire risk assessment, 9540A, you name it. There's a lot of questions that are asked that both Jim and Sharon brought up. So how do we get to a holistic approach? How do I integrate all those parties into something that is appropriate for the risk? There's obviously a big difference for something that's located in the deserts of Arizona versus a downtown urban environment. So those risks are appropriate. So we have to look at that. How do we minimize scope split where the container's doing one thing, the site's doing something else, the equipment doesn't marry up, the HMAs have all got to be the same. So it is a jungle of information. So one of the things that I looked at too, since I tend to spend a lot of time looking at this gas production and explosion impacts, if we take a relative impact and they designed a deflagration system for this unit in McMicken, we probably would have designed it on a 1 or 2 cell failure. The door would have been more than adequate to vent that pressure based on that design. But ultimately, as we saw, there was a lot more pressure, a lot bigger failure than what would have realistically been designed. So big part of what we try to do is give options and look at failure modes. How far do they go? What's reasonable? Do we look at a cell, a module, a rack, an installation? And what do those failures look like when we come to protection? I'm not above borrowing slides to prove a point. There's a lot of great information out there in the industry. So this particular one gives you kind of a graphic presentation. We have a cell failure and it doesn't ignite, but we accumulate gas and it ignites. We have a cell failure, it ignites immediately, the fire goes out, it probably ignites again. So an explosion is an inevitable process that we need to take into account and figure out how to measure. This is kind of a relative input on what it may look like from a residential, what gas volumes can accumulate. From a residential Powerwall type system, it's fairly low volume. What we saw in Surprise, Arizona, it could generally create over 400% gas volume. A small container, we get to those gas volumes real quick. So part of what I've been looking at and working with is the explosion risks within 855. I do sit on 855. I do belong to the SDP for 9540, number of safety councils. So spend a lot of time trying to work with people and educate. What we're seeing is some guides that are going to come out, which will hopefully give people some data on how to appropriately evaluate and what to look at. Longer duration events, we got to figure out how we're backing them up. We've added a lot of information to the explosion chapter and the supplemental information to give guidance for that 68 explosion, 69 venting requirements. We're looking at small containers. The industry is moving that way. So we've got to figure out how to effectively mitigate those small containers. It's really hard to deal with gas production in that small space. Also, debris and shrapnel. What's that going to look like? How do we manage? I don't think the codes are there quite yet. And a big one is increasing the hazard mitigation analysis and engineering of analysis of gas production. How do we get to a better solution that gives us a little bit more safety margins? This is a big one. I think it's ultimately gonna go through, but I question if there's not gonna be a lot of pushback in the industry. This is actually retroactive. It goes back and says any systems that were not 9540 shall be required to have an HMA and be upgraded. So what it probably means is you're gonna have to go back and look at 68 and 69 on existing facilities. It will be controversial, acknowledged. Give some input if you feel appropriate. We're always looking for feedback. So we see a lot of competing requirements introduced into this code cycle. We kind of talked a little earlier that sometimes the codes are way behind. So what are we implementing? Best practices? There is knowledge in the industry. It is hard to come by, but does exist. Or do we just meet codes? I think that leaves us a little open. If we know that there's a better way to do it, we need to look beyond codes. We are still struggling a little bit. What are those best practices? What are the safety factors? If 9540A says we only had one cell, didn't propagate, do we evaluate on a single cell, or do we add a safety margin to that and evaluate our explosions based on an N+2, one cell plus two, or one module plus two modules to come up with a anticipated event? We are in cycle with 855. Public comment is out. It is, I think, the end of July. Please take a look. We can use any help, recommendations, data. Go on, take a look at it, give us feedback. It's much appreciated. So I still believe, the events are rare, but they can be significant. What are we looking at? Fire or explosion? Big question in the industry now, what is a safe approach distance? Well, it's highly dependent upon the failure mode. Make sure you're at cover. Engage safety early. Bring them on. Bring the fire department in. Bring your AHJ in. Make it part of the early planning. Any one technology is probably not going to be adequate. We need layers to help mitigate the failure. Now, I'm not opposed to let it burn. I'm perfectly acceptable with that strategy, but it does have to be in the right environment and the right risk. Do not engage life and safety. An asset is not worth a life. Let it burn. But it does mean, in urban environments, you're probably looking at some robust protections. We're still learning. As Sharon mentioned earlier, technology will continue to outpace the codes. So there's a lot of good things happening in the industry, but they're not very well covered in the code. So it's an education again. How do we teach the industry, the fire marshals, the fabricators, what works and why, such that this new technology can be implemented? So failure to plan. I have no idea what anybody was thinking on this one, but their solution was just to punch a hole through the door. So it is sometimes we do find ways to get around it. It's that unintended consequences, but absolutely plan for it, investigate it, make sure you're adequately covered. So there's my wonderful image again. I do thank you guys very much. It does hopefully gets us through fairly quickly. And any questions or conversations?
All right, Paul, Aaron, and James, that was outstanding. We really appreciate the thoughtfulness and care that you put into those presentations. Many of you have already submitted questions, the attendees, and you can continue to ask questions during the Q&A session, as well as by using the question chat box in your browser. So I'm going to start to take a look at some of these questions that have come in. This one I think was addressed to James, but I think Paul might also want to comment on it. The question, the comment, it seems like in module and unit level tests, only one cell is induced in thermal runaway. Why not induce thermal runaway in an entire module at a time, especially if there is no propagation when only one cell goes into runaway?
Well, number one, that's a mistaken interpretation of 9540A. The standard says you are to force propagation. If you can do it with one cell, great. If it takes 5 cells, do 5 cells. Force the failure. And again, the whole purpose of 9540A is to force a failure so that we can figure out what happens and just plan around it. When people only test one cell, they are not compliant with 9540A.
Yeah, Jim, because I look over a lot of these reports, I would say part of the struggle in the industry is that a lot of them are run under Rev 3, which didn't require that propagation, and 4 does. So the industry's struggling with that a little bit to how do they get over that. and ultimately, does it catch fire? If it doesn't catch fire and just produces gas, have we met the intent? And as a fire protection engineer, I would say yes. If you've got propagation, you didn't catch fire, you've still run a successful 9540A test. So that's the data we look at, the gas production that we want to be able to come off of a module cell, whatever that level may be, in order to apply the engineered solutions.
But again, if you are getting either flame or flammable gases, the electrolyte gases, out of a cell or a module or unit, that is, not you don't pass at that. You don't, I wouldn't say pass. There are steps you go to. If you get here and there's no flame, no gas, you can stop. That's not a stopping point.
Yeah,
Okay,
I think you have to also look at it from the standpoint of what is the reason we're running these tests? We're trying to get the information that provides the information that the fire protection engineer needs in order to properly design how you're going to suppress or extinguish. And if you don't get it to go into thermal runaway, you don't get that data. So looking at the ultimate reason for the test is, I think, a better thought process.
Also, as Paul mentioned, we are constantly learning. That's why we're in the 4th edition of 9540A. As we went from 3 to 4, it's because we've learned more. And when a testing organization uses older versions of the test, that defeats that whole shared knowledge safety gains process.
Yeah, one of the things I look for.
I'm going to cut off this fascinating colloquy in order to accommodate some more questions. I've got a couple of questions that are related, so I'm going to combine them. The first one asks, has a cause been determined for the Beijing battery fire? And the second one is, what is the best way to obtain information about major incidents that have occurred? Is there an organization or agency collecting data?
EPRI is keeping a database on events, but they obviously have to hear about them and get some information. So I would highly recommend EPRI as an option.
As far as Beijing goes, we know what the kind of system was installed. We know the chemistry involved. We don't know what caused it. I mean, you got 25 megawatts worth of recycled auto EV batteries that went bounced around the streets that were just assembled but not tested in accordance with something like UL 1974. So I have issues with how it was put together, but what caused it, an electrical short, we don't know. And I don't think that the authorities in Beijing are going to tell us.
That's a fair assessment. Another question, this one's really interesting, particularly given some recent articles in the news. What are the codes related to the cybersecurity of the battery energy storage system, as that can also be a case of fire or explosion by hacking?
Well, I can certainly say that it's a major concern to someone like SRP or any utility. I know initially when we were putting some energy storage into play, we ended a conversation because they were doing all the controlling via the cloud. So we were utilizing isolation as a manner to protect against the cybersecurity attacks, that sort of thing. It's certainly an area of great concern. And I think you're going to see more attention to that in the future in general regarding the grid and all sorts of generation and energy storage.
I'm currently working with the EPRI team. They have a 2-person team addressing this topic at the EPRI headquarters, and UL is working with them. There are a variety of UL standards for cybersecurity. That's not yet in code or standard to apply to energy storage, but I'm a member of what the FBI's InfraGuard program. That's to protect infrastructure, and that's like, you know, water, transportation, or energy in this case. And that's a big concern on the part of the federal government. I mean, just if somebody could hack a major supplier's energy storage systems, much as say the pipeline in the Southeast got hacked last week, you could just crash a grid in a heartbeat. So we're aggressively but quietly moving ahead on that.
Okay, thank you. That interesting material. I've got a bunch of questions. This will be the lightning round for our contestants here. I've heard that only UL can perform the 9540 test. True?
9540 can be done by any of them. And I'll tell you right now, for 9540 certifications, we are not the leader in the number of those that get done. So, and then when it comes to 9540A testing, we are the dominant player in that because, quite honestly, the two biggest fire research centers in the world are UL and then FM in Rhode Island. So we dominate that area, and we've been driving it for some years. I will tell you, in my long-range planning sessions I've been going through this last week, oh, trust me, the Intertech, CSAs, TUVs of the world are actively expanding their capability in these areas.
I can also just quickly add that one of the rules in writing the Icc codes is you can't be referencing something that's, you know, a prior, sorry, missing the word, but something that's proprietary to one item. So it has to be a test that can be used by multiple people to comply, or it couldn't be referenced in the I codes.
Okay. This is really kind of getting tough here. Sharon, any indication that codes will ever subdivide lithium-ion batteries by chemistry, for example, LFP versus metal oxide?
Yes, I think that's highly probable. I think and this is where the public involvement is so important. If those industries came to the Fire Code Action Committee or to the 855 committee and said, here's some test data. We want to show that this particular chemistry is much safer than this other lithium general category. If they bring enough of that data to the committees, then the committees are more than willing to add one more line to that chart and change the quantities. In fact, they did it just recently with some zinc. So yes, that's quite probable.
Okay.
Under 1973, we test all kinds of batteries, everything from the 25 plus different lithium-ion chemistries to flow batteries and everything else get tested, and they also get tested in our 9540. We have, it's not all just lithium-ion.
All right, that's great. Just a couple more questions because unfortunately we are running out of time. And I'm gonna, again, pair a couple of questions because they run through some similar content. Question one was, what approach should a utility that has no fire protection experts take to ensure safety for a large volume of energy storage implementation? Hiring consultants for all the projects does not seem like an effective solution. And sort of a related question, are there courses or conferences that address safety in design, construction, operation of energy storage systems? And I'll let anybody answer or comment on those.
Go, Paul.
Thank you. You know, the courses are limited right now, unfortunately, to things like ESA and EPRI. There are a lot of online things right now. I would just, UL, SFPE, almost everybody across the industry is trying to learn. Keep an eye out, sign up for the groups. That's the best way to get information. You know, I would still highly recommend a consultant at this point. There are some good people out in the industry. The safety is the first priority. Damaged is going to cost you a lot more than that consultant would. So the other thing is maybe work with that consultant to establish specifications. A number of big utilities are writing their own spec, but engaging, and they're sharing to some extent as well. So there's probably some people through, again, EPRI, ESA, that are willing to share information of what their spec looks like. I know Sharon's got some, APS, Duke. A lot of those companies are writing spec. Follow their lead, ask for their help, but I would encourage a consultant.
Also, if you're in a utility, the EPRI has a very nice spreadsheet they will give you in a heartbeat that lays out the things you should be thinking about when you're doing energy storage, everything from technical specifications to site issues to safety, what testing you should do. It's all provided to you in that, God, it's a massive spreadsheet with a zillion tabs in it, but it's really nice work. And if you're a utility, you're probably a member of EPRI, and the Energy Storage Committee there will provide that to you.
Yep, good point, Jim.
Yeah, there's two committees in particular, UL 95-4, excuse me, panel 94 and 197. Both deal with energy storage and some best practices. I also wanted to mention that NatBat is also developing for their website a spreadsheet of all of the universities, community colleges, trade organizations, you know, NFPA, all of those, and the different training programs that they're have available, and that we're looking to have that up on the NatBat website so that people can start to, in your hiring, look at people who have had energy storage and energy storage safety training. But I think there's a lot out there. Certainly some from NFPA too.
There's a coalition of providers who recently won a $2.1 million grant from the DOE. That's International Code Council, UL, just a bunch of us came together to do training for safety training for AHJs and building owners as well. It just got awarded, and that'll be rolling out in the coming months.
Yes, and I will I'll also add that ESA is involved with some of those efforts, including through its corporate responsibility initiative. But I am afraid we have arrived at the end of the hour, and I would like to thank the presenters for a very informative session. Before we conclude, I'd like to remind you to register for the seminar on June 16th and 17th, and also to save the dates December 1st through 3rd for the ESA annual conference in Phoenix. Please stay safe and healthy, and have a great rest of the day.